5.3, scientific notation. So a long time ago, science people, because math, we get our own notations and stuff, but science people wanted their own notation, so they came to the math people and said, we want our own, and then we made it, and then they took the credit for it, you know what I'm saying? This is all fake history, by the way, but in any case, scientific notation is good for extraordinarily large numbers or very, very, very small numbers, which then allow us to, they allow us to take little shortcuts when making calculations, but there's another way to make shortcuts right here. So we'll see how it goes. All right, scientific notation. This right here is a very nerdy way to say what scientific notation is. Well, it says normal language. I still think it's pretty nerdy, but that's just me, okay? So, first off, you have to have a ones place value, nothing to the left. No tens place value, no hundreds, nothing to the left. No place values to the left of the ones. And in the ones place value, you have to have not zero, okay? You can have as many decimal places as you'd like, depending on how many figures you would consider to be significant. But for the most part, it doesn't really matter how many decimals you have, at least mathematically speaking, right? Scientifically, they'd say there is a certain amount of significant figures. And then you multiply this by base 10 to some power. Any exponent will do. It could be zero, it could be negatives, it could be positives. It could even be decimals, technically speaking. Not that it usually is, but I suppose it could. But this would be the basic format for scientific notation, okay? So just as a kind of a quick exercise, because I'm looking right now, and I'm the number's constantly changing on my screen right here. This is the number, 29, 927, and what is today? October 28th, 2001, 329. And the other numbers are changing so fast right there that I can't actually keep track of them. Maybe this is a hint as to what number I'm looking at. That is the U.S. national debt right there, which used to not be so big. I mean, it's always been pretty big since I've been doing this activity, but it's now extraordinarily large, and it's very easy to just change this number into what is considered scientific notation. Because, like I said, it's usually useful with very large numbers such as this, okay? So, remember, the first place value has to be not 1, so we just pretty much look at the number furthest to the left that's not 0, boom, 2 right there, right? So I would say this is going to be 2 point, well, I know it's kind of off, oh, too many 9s right there. 992732996. And while there are other zeros there because I just kind of forced them to be there, I'm not going to list them. Now, you could say, well, that's 29 trillion, by the way, almost 30 now. Some people would even say, well, this 100,000s right here, it's pretty insignificant when you look at $29 trillion. Now, if that's you, that's hooray for you, okay? But to me, I still think that 600, that number right there is still pretty significant, at least in my world it is. In fact, even all these numbers to me would be pretty significant, so I would imagine to college students, these would be significant. In any case, I'm going to keep them in here because they are significant, although some people would say, can't we just round this to like 2.99? Sure, you know, if you're saying that, what is that, 10 billions right there is insignificant to you, sure, feel free to do that, okay? That's up to you, but then we'd have to multiply this, like it says, by 10, base 10, and then to the exponent. Well, right here, we got to figure out what exponent we'd have to multiply or use with base 10 here. And since it's base 10, it just means that we're looking at all of our place values, which to me is very nice, right? Because our place values are based in tens. So let's say, see, they got the ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, 100 billions, and then 1 trillions right there. Well, how many place values was that, by the way? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 place values right there. And so, well, just to give this some meaning, boom, there you go. And that would be that number that I wrote, even though it's now bigger than that, according to usdebtclock.org. But in any case, that's what number that I wrote as scientific notation, okay? So what does it want us to do? It wants us to rewrite now a scientific notation number in, it's what it usually says standard form or standard format, standard notation, something like that, okay? As a whole number or decimal, okay. Now I'm going to show two ways to do this, and you'll choose which way that you like the best, okay? So what is this? Remember, you got the ones place value, the decimal, doesn't matter how many decimals are there, times base 10 to the power of 7. Oh, that's very nice. Here's what I like to do if I'm doing it by hand, 8.12, and then this exponent here is positive, right? So I say, well, that's a positive 7. And since it's positive, that tells me that I need to move the decimal seven to the, since it's positive, it goes to the right. Which means if that exponent were negative, then I would have to move the decimal to the left instead. To the right, that should say to the right, but to right, that's fine. 1, 2, 3, 4, 5, 6, 7. It's really 7 place values. If you ever get any empty place values like this, feel free to just fill those in with zeros to hold those place values. Now, if I write this out again, you have 8, 1, 2. So I'll move the decimal over, 1, 2, 3, 4, 5 zeros. And right now, that decimal is about right there, okay? So for those of you that like to see those commas to separate the periods, that looks like 81,200,000. Okay. And that'll do. That's good. Well, as promised, I said there's a second method, and it's a calculator method. So here's what you can do. You would type in 8.12. Now there's a button. You don't have to type times 10 to the power 7 because there's a scientific notation button. It's 3 buttons above 8. It looks like this, times 10 to the power of n. Right there. It's it's immediately to the right of our n over d button. And then you'll see on your screen that it's now waiting for you to enter the exponent, which is 7. So type in a 7, push enter, and then it will change that into standard form for you, okay? Which is the same, that's the same thing that we got right there. All right, well, here we go. So I'm going to do this by hand, just so you can see what's happening and why the calculator is doing what it's doing. Awesome. So 8.379. But again, this negative 7 right here is the same thing. It's just telling us you need to move, because it's negative, move the decimal 7 place values to the, now it's negative, so it's going to the left. That's kind of small, but I think it's still kind of legible. So I go back, right, and I say, well, I'm going to move it 7 times to the left then. 1, 2, 3, 4, 5, 6, 7, and that's where the decimal will be. All these empty place values will then be zeros. Okay, so what do we end up with? Decimal. I got 1, 2, 3, 4, 5, 6 zeros. Then we have the 8, 3, 7, 9, like this. Okay, and yeah, I mean you're welcome to put a nice 0 out there in the front if you'd like, but it's not necessary that you do. You'll get full credit either way on Canvas. So, negative exponents will move the decimal to the left. Positive exponents, like the last example, will move the decimals to the right. There's another method. It's the method that I prefer. Just type it into the calculator. It'll do it. Well, will the calculator change this number right here into scientific notation? It will, but let's save that. Let's save that for a second, okay? Because we can do this by hand. It's not even that big. Well, it's a pretty large number right there. Let me see how many zeros we got here. Let's make that bigger, in fact. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, which means we need the decimal right between that 6 and 0. So it should end up being 6.0 something times 10 to some power. Okay. Well, how do I know the decimal goes here? Because remember, scientific notation, you have to have only the ones place value, non-zero number, okay? So I know it has to go, the decimal has to go immediately to the right of whatever non-zero number is furthest to the left. Okay, well, I just counted, we would have moved it 13 times, right? So this is where it is, and we moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we're gonna move it 13 times. So I'm gonna put a 13 here. It's just a question of, is this 13 going to be positive or negative? Okay, well, since this number right here essentially is bigger than 1, we know it's going to be a positive 13. That's done. Okay, now if it were less than 1, meaning some kind of decimal value, that is what will make this exponent a negative. So, like we just saw in the last two examples, now that it's in scientific notation, then you'd say, see how it's positive 13 here? To change this back into this giant number, I guess that'd be 60 trillion. Then you'd have to move this decimal 13 times to the right from scientific notation, like we did 2 examples ago. Yeah, but I said that the calculator would do it for us. It will. Okay, so now you have to reprogram the calculator. You have to say, calculator, I want my answers in scientific notation, and then it'll be like, all right, everything will be in scientific notation. We'll see, okay? Here's the button progression. You gotta, actually, I'll kind of make this slightly color coordinated. Mine's green. You gotta push the second button. Nope, you don't have to. Well, I take that back. You don't have to push the second button. You just push the button to the right of second button, which says mode. My lowercase letters aren't very good, okay? Now, on your screen, just at the top, you see degrees, radicals, and gradients. And then right below that, you see norm, psi, and eng. What we need is psi, S-C-I, that is scientific notation. So from there, I'm going to use the cursor to go down. And then I'm going to use the cursor to go to the right to highlight psi. And then I'll push equals or enter, whatever. And then you just got to get out of this, I push clear. And this will take me back to the home. I want to say home page, but I don't know that that's necessarily what it is. It's just the home screen, okay? Okay, now I'm back in there, right? So I'm going to type this in. 6, and then remember, there's 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I push enter, boom. It changed it. It's not even showing the 0 on my screen, but it did change it into scientific notation. In fact, go ahead and just push 9, enter, and it'll change that also, just any number. It'll change into scientific notation. Which means if we need to start calculating, which we will very soon, just for this section, by the way, if we need to start calculating in scientific notation, if you just put things in scientific notation, whatever notation you use in this, it'll say, here's your answer in scientific notation. A true scientific notation, which I think is pretty sweet. Because they didn't used to do this garbage when back in the day. All right, well, we won't always be using scientific notation. So here is the button progression to get out of scientific notation. It's kind of the same. So you're going to use mode. You're going to push that mode button. And then you're going to use the cursor because you got to go down. Down. Push. But what you want is norm, like an episode from Cheers. So you just push equals and clear. And then it'll take you back to the home page or the home screen, and everything after that now is now in normal mode, okay? And you can go back and forth between scientific notation and normal mode with this button progression, okay? Now this number right here, it's not in formal scientific notation. And why is it not in formal scientific notation? Because, remember, the decimal one has to be right after the 9 here, but it's not, okay? So what I'm going to do, I'm going to take this 948, and I'm going to make it, because remember, that's where the decimal should be, right? I'm going to make 948 9.48. Okay, well, that means that where the decimal was, right here, just to the right of 8, which was the ones place value, I'm now changing the 9 into the ones place value by moving this decimal to the right. Maybe I should just put right 2. Okay. Now you'll notice here that the 948 was made smaller into 9.48, okay? Now, what this means for us is that the exponent, because remember, all we did was use our place value system in order to make that large number smaller. That means that then the exponent will get bigger by, remember we moved it 2 times to the, sorry, that says the right, that meant it's supposed to be to the left. Come on, Sal, man, gotta figure this out. We moved it 2 times to the left. That means that because we made the big number smaller, that means that now we're going to go in and we're going to make the 7 bigger by 2. Okay, so since I moved the decimal 2 times to the left there in scientific notation, I'm going to add 2 to the exponent. What this does is it changes the way this looks into formal scientific notation, but without actually changing the overall value, okay? Because if I had just left this as 10 to the power of 7 times 10 to the power of 7, yeah, that completely changes the entire value. But by adding 2 to the exponent right there, nope, that did not change the value, but it did change the way it looked. 7 plus 2, boom, I get 9. And now it is in formal scientific notation. I apologize for putting the right there. That was clearly to the left. Now, would the calculator have done that for us? Yeah. Remember, if you're in scientific notation, which I still am, I could have just typed in 948 times 10 to the power of 7. And if I push enter, it says, hey, you had that all wrong in scientific notation. I will give it to you in scientific notation. Thank you, calculator. I like that shortcut. All right, what about this one? So it kind of looks like scientific notation. That's the tricky part. And yeah, sometimes math people think they're funny. It's pretty nerdy, though, to think, hey, we trick people by not putting this in formal scientific notation. All right, freaking jerks. The decimal needs to go right here. Okay, now this is a pretty small number, not because it's negative, because of the decimal. It makes it pretty small. What we would like, really, is for the decimal to be between the 9 and 8, making that 9.87. Well, if that happens, then we took a small number and made it bigger. Okay. Well, how much bigger? Well, we moved the decimal. This time it is to the right. 1, 2, 3, 4 times to the right. That's pretty good. So that means that now there's an inverse relationship here. That means that the exponent will have to get smaller by 4. Okay, and by smaller, I'm just talking about subtraction here. So I'd take that 10 and subtract 4. So our 9.87 is still going to be multiplied by base 10, but 10 minus 4 there is then 6. 9.87 times 10 to the power of 6. And that now is in formal scientific notation, which the calculator would have done. Oh, I forgot. Yeah, I did forget the negative. Don't forget the negative in the end, though. There we go. Negative 9.87 times 10 to the power of 6. That now is correct. So there's another method. It's a little bit longer in my opinion, but it could be useful, right? So you could go back to the first couple problems that we did where we're just changing this into standard form, not scientific notation, just standard form, right? So you see the power of 10 is positive, which means that we'd have to move that decimal to the right 10. So I'd rewrite this, negative 0.000987. Then I could move that decimal to the right 10 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then all these empty place values, that's a 0, by the way, are zeros. So we end up with 9,870,000. Yeah, just like this. And then if you wanted to, from there, you could change this into its formal scientific notation. Again, the decimal has to go between the 9 and 8. So you have 9.87. You're welcome to put the zeros there. I'm just not going to because it's too much work. And then times 10 to what power? Well, we move the decimal 1, 2, 3, 4, 5, 6. 10 to the power of 6. Oh, sorry, it was negative again. I almost forgot that negative sign again. Same thing that we had before, just in it. We went all the way into standard form here, and then we went back into formal scientific notation. All right, can we operate here? Yeah, we can. Will the calculator do this for us? Yeah, it will. And it does want the answer in scientific notation. All right, that's great. So here's what I mean by scientific notation. It allowed science people to really take big time shortcuts in it instead of actually, doing a lot of stuff by hand, especially if you're stacking and multiplying and stuff. Not that I think that a lot of them do, but here's what we can do is we can kind of use the commutative property to take the non-base 10s, which in this case is 8.2, and just multiply it by 8.1. It's the commutative property right there, which when I do, I get 8.2 times 8.1, enter. Oh, I'm still in scientific notation. Going back into normal mode here, which gives me 66.42, okay? And then what we end up doing is we use exponent properties to work with this base 10 stuff, okay? So that's 10 to the power 33, then times 10 to the power 16, two base 10s, which then would be 10 to the power of 33 plus 16, which would be 10 to the power of 49. Now, the problem with this is that it's not in formal scientific notation because the decimal is not between the two sixes right there, which it needs to be, right? It needs to be right there, which means this one is going to make that big number smaller into 6.642. So I move that to the left one, which means I would have to add one to my base 10 exponent. So times 10 to the power of now 50. But like I said, the calculator would have done that for us if you remained in scientific notation mode. So I go back to scientific notation mode, 8.2 times 10 to the power of 33 times 8.1 times 10 to the power of 16, enter. Yeah, and I got just what we see here, 6.642 times 10 to the power of 50. And really all I'm doing right now is checking to make sure I did that work correct. But calculator would have done that in the beginning, okay? So you can see back in the day when there were no calculators, maybe a good abacus or whatever the heck they're called, that saves you a little bit of time right there, which I think is pretty handy. I just don't know how useful it is in modern world. All right, so this, by the way, is a fraction, which indicates that we are looking at division. And so I got 1.92. I'm just looking at the numeric part. 1.92 divided by 1.6. Now, again, I'll go to my calculator for this. 1.92 divided by 1.6. And I got 1.2 from that, 1.2. And then we got to work with the base 10s, right? So base 10 to the power of negative 11. And that would have been dividing by 10 to the power of negative 3. But the bases are the same, base 10s, which means we're going to take the two exponents. The first one, negative 11, and then subtract the second one, negative 3, which ends up being base 10. So 1.2 times base 10 to the power of negative 8 on that. And that right there is already in scientific notation, so it's done. But again, if you're going to use the calculator, like I would like to, I'm going to use the n over d button to show it is a fraction. 1.92 times 10 to the power of negative 11. Then I go to my denominator, 1.6 times 10 to the power of negative 3. Enter. What do you know? Gave me the exact same value, which I think is pretty cool. If a star is, what is that? Millions, billions, trillions. I guess I'd call that quadrillions, but I don't know for sure. 6.71 quadrillion meters from Earth. How many seconds does it take light to travel from the Earth to the star? That's in meters, I guess. Enter your answer in scientific notation. But the speed of light here, we're going to assume that's in meters, because I don't know for sure, but whatever. 3 times 10 to the power of 8 meters per... Well, they probably should have given us a little bit more information that, just in case we wanted to use some dimensional analysis, which for some reason makes me feel good inside. In any case, so how many seconds does it take light to travel from Earth to the star? Let's see, how many of something is in something else? That sounds like a division problem to me. Although dimensional analysis, by the way, it would have taken care of it. Well, I guess I probably should have given myself more space as well, which I will do now. So I'm going to take that big number. Instead of rewriting, I'll just use some technology here, which is in meters. And, let's see, yeah, I'd have to divide this by the speed of light here. You know what? Take that back. I'm just going to use 3 times 10 to the power of 8, like this. And that would be meters for every 1 second on this. I am going to use some dimensional analysis. Maybe I should, maybe I shouldn't. I don't know. If you don't know what dimensional analysis is, you don't necessarily have to, but it may help us to figure out why we're using division as well. Because if you by chance use the wrong operation here, you'd get meters squared per second. I'm not really sure what that is. I mean, meters per second squared is the acceleration, but I don't know what meters squared per second is. It doesn't make any sense. Remember, the final answer here needs to tell us how many seconds it is. Now, if I divide, why does that make division work here? It's because we don't divide fractions. We only multiply them. And yes, your calculator would have just done this. If you change the operation to multiplication, you have to reciprocate the fraction, the second one, which then makes that now 1 second per 3 times 10 to the power of 8 meters. So for any of you that are going to end up going into some kind of physics, usually, well, this could end up being helpful, but maybe not. So what happens now is that the meters in the numerator, the meters in the numerator will phantom 1 with the meters in the denominator, which it can do that with labels as well. And see, now we're just left with seconds. So you could type this in. Really, I'm just going to take this very large number and divide it by 3 times 10 to the power of 8. That's an 8, by the way. Sorry about that. So what is this? 6. Oh, 6, 7, 1, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then I can even make it a fraction with 3 times 10 to the power of 8. Enter. Oh, it is in my calculator was already in scientific notation. That's pretty good. It ends up being 2.236. It didn't say where to round. I'll give it one more decimal place. The sixes would just repeat, and then this is times 10 to the power of 7. I did it right there. What the heck is that? So 3, it'd be like 20 million, 22 million-ish seconds. That seems kind of slow for the speed of light to me, but whatever. Yeah, there's a word problem. Don't forget to label your answers if you're doing this by hand. You know, if you want full credit anyways. Seconds. A sun in a distant galaxy has an estimated mass, it's a pretty big mass, of kilograms anyways, and the Earth has this mass. How many Earths would it take to equal the mass of the sun? Write your answer in scientific notation. Well, how many of something goes into something else? Once again, that is a division type problem. I'm not going to use dimensional analysis on this one. You could, by the way. For those of you that were really geeking out about that, like I would, because I'm a nerd, I'm not going to for this one, okay? So I'm going to take the mass of that, whatever that sun is, and since I want to know how many Earths are in that, yeah, of course, that means that this, well, maybe I would technically need to put that in parentheses, unless you're going to put it into a fraction form. I'm using just straight division, though. So this is the distant sun. We'll just call it sun, because distant is kind of a big word. So there's the sun. Some sun out there somewhere has this kind of mass. How do they know that? I don't know. But you can say whatever you want, I guess. Okay, so here's the distant sun. We want to know how many Earths are in that sun. That's why we divide this by the value of Earth here for kilograms. I don't really need the labels right here. Now, if you want to use dimensional analysis, all you would do here is make this, it's kilograms per Earth, which kind of sounds weird, but that would work right here to make that a fraction, okay? Then you'd flip it, and then you'd multiply, but there's Earth. Now, as much as you may want me to, I'm just going to use the calculator to do this one, okay? So, well, parentheses first, 2.84299 times 10 to the power of 35, it's a big number. Close that parentheses and divide this by new parentheses, Again, if you use the N over D button, it'd give you the same answer, but 5.972 times 10 to the power of 24 here. Oh, I almost closed my parentheses in the exponent. Make sure you get out of exponent mode before you put that parentheses there. Enter. Oh, there's the number it gives me, 4.76. It does want the answer in scientific notation. I'll do one more decimal place. I have 0.5 right here, and since that 5 is right there, that means the 0 in the thousands place value will have to add 1. So it's 4.761. That my calculator is showing times 10 to the power of 10. That's how many Earths, the weight of Earth, or mass. That's how many Earth maths you would need, Earth masses you would need to fill up that, whatever sun this is. Some sun out there. I assume this is made up. I don't know if there's an actual sun out there with that weight, but could be, I guess.